Today it is the class number 28, 2020, April 21st, and we are in advanced steel structure. And from the last class we left off, we are covering the paper here. It is fundamentals of beam bracing. There are many more issues relating to the stability of the structures, bracing, beam columns. But what we had covered in this course, I think I cover you the important parts, something that is necessary for you, something that is going to be the basic understanding that you can make use of it to understand some other things if you come across, if you want to check into the details of everything. There are so many papers that are listed around here in this one, and you actually can just track back and take a look at them. Anyhow, if you do not have time, and when I have time in the next semester, I can just come into the detail of things that are omitted in this semester. Well, this is generally the regular class time that we have allow us to just come this far, around this far, right? Examination will be on 29th, so it is approximately just 1 week from now. And if we come into the detail of each paper, we cannot afford the time to finish up the whole course, finish up the course before the exam time. But it could be like the appendix lecture, sort of like I have more time because I do not have to cover the old things I used to cover. Then I talk about the new things I never cover, and that's gonna enhance your horizon. So you can come back, feel free to come back and check it out if there is anything that is still slipping through, and you can just enhance, you can just improve your understanding, and it's sort of fun. I think sometimes you don't want to watch the music video on YouTube all the time, right? For a whole day long. It's gotta be boring. So you need something which is just to change the atmosphere from the music video or some comedy channels, series, into some part that is academic related, and it is an update for your knowledge. Actually, it's not a new knowledge, but it's just the part that is augmented from the regular class. So the course can be continuously improved regardless of where you are, regardless of the conditions you are, like you are no longer a student, you are working somewhere. You can just come back and grab this knowledge and just enrich yourself. Okay, so where we left last time is about here at the page 16, and lateral brace design is gonna be the issue that we're gonna pick up. So I think we have seen this part already. I highlight something already, but now let's come down here. This is a fundamental equations for the brace design. So I think you remember from the winter bracing, winter used the K equals to the PE, right? 2 PE over LB something, where the L is a unbraced length between two supports, right? And PE is the maximum force we need to mobilize in a column, and the number 2 actually it is changing like from 2 to 3, from 3 to 3.1 something, and 3.6 something, and all these number 2, 3, etc. we used to talk about, and we use the codes I made to develop, to come up, to show that the number is fitting with all of this when we put the sufficient brace stiffness. All of this you can play with it and you can convince yourself. And if you don't want to convince actually yourself, you can just, in the design, you may not want to, if you are stubborn like me, so if you don't want to go this way and believe in the number, for example, if you have like multiple bracing points, like 7 points, and the number you get is 4, it is between 3.6 to 4, you want to find a precise one. Well, 4 will be conservative, of course, but you want to find a precise one. You can play around with the codes like that, and you can come up with the optimal brace stiffness. Sometimes you are encountering the case where it is not just the column, it could be the platform, the plate, and parking lot, underground parking lot, which is supported by the floor, and then the floor is supporting the lateral earth pressure under the compression. You might have the column. The column might be considered like the brace for you. Well, generally column is very stiff, of course. So many situations that you should be able to apply the knowledge, apply the techniques we learn. And we are not learning the formula. We learn how the formula is derived, how the formula is formulated. The formulations of everything in this course regarding the stability issue. I think we are in the detail. We are from the root. So I hope that as you learn from the root, you should be able to come all the way back there and be able to start from the foundation. Okay. So for this one, the beta, okay, or the K stiffness is given as shown. The beta or the K is equal to Ni. The Ni is the number over here. The I subscript depends on the number of brace you have. For example, if you have 2 braces, then I is equals to 2, right? And then you gotta have the 3 to plug in to here. That's it, as simple as that. And now I think the internet connection was not good, but it came back, right? So the basic idea of designing the lateral brace stiffness for the beam is actually pretty much like the column. In the beam, you see this is the paper for the beam, but you see the identical formula as the column, but it is the fundamental one, it is the starting one. So there will be some other components added on top, okay, into this one here. But okay, let us take a look at the issue. So that K or the beta we had for the column, why are they in here for the beam? Yeah. So if you think of the beam under the bending, and when the beam buckles from the lateral torsional buckling, right? So what happened in the top flange? I shouldn't call top flange because it is not generalized. Actually, you should we should call it the compression flange, okay? But it could be on the top, it could be at the bottom. But if we think of the simply supported like this, the top flange here is under compression, whereas the bottom one is under tension. So the part which is under compression is the part that undergo the unstable. Instability is in the top flange. So that means buckling is there. So as we know that under compression, the top flange buckling, the top flange as it buckles, when it buckles, it goes laterally, and the bottom does not go like the top flange, so it causes the torsion in the same time. So that's why we have the lateral torsional buckling in the beam problem. Okay, so the resistance or the restraining has to be provided to the top flange. I shouldn't call top flange, right? Compression flange. And as we went through this paper in the last class, we saw that the effective way to stabilize the beam is to provide the brace to the compression flange. We accept that. We saw numbers of the simulations that shows the consistency of this conclusion that I just talked. So as it is needed to, as the top flange is going to be to mobilize the full capacity in compression, that means it's gonna go up all the way to the buckling load of the flange under this given condition. So if this is an example, if we restrain, well, of course we have the 2 points, and then if you want to brace, I shouldn't okay, I put the brace like this as a spring. So that means we are expecting that this is going to form. Okay, so we brace at the middle point, and then it should be buckling, forming the half sine curve over the L/2 length, and this is the buckling load of the flange, top flange only. So the P is computed accordingly. The P is coming from the flange itself, pi square EI over LB square. The I here, IYC, stands for the compression flange, and it is the IY. What is the IY? So this is the X, this is the Y. So Ix is the moment of inertia about the major axis, as we know. The Iy is in about the minor axis. For the Iy, the contribution mostly come from the flange. The web does not contribute. It is it is just a fraction, it is just a percent, a single digit of percentage. It is nothing. All right. So what you expect is the full mobilization of top flange capacity, and that turns out to be the IY, yeah, divided by 2. We're gonna need the capacity of the top flange only. So bottom flange, you have nothing to do, it is under tension, so you are not worried. You're worried about the top flange. Then IY is actually the whole section IY, but as I said that it might be simplified so that the IYC is equal to IY of the whole section divided by 2. You halve it out to get rid of the bottom flange, then you get the part under compression only. Alright, and it is here and it is explained here that it is just IY over 2, and there's nothing about this more than just we halve it out. Okay. Alright, and what else? LB explained already. This NI, actually NI is given in the next page. So number of brace, 1 point bracing, the coefficient is 2. You brace 2.3, 3.41, 3.6, and more than that you get 4. So these are the rule of thumb number, and you can just make use of these numbers. Well, it is quite easy to, it is just a handy number, it is just a rule of thumb number. It is okay. So pick it up, or if you do not want to use this, you can this is the option. So this approximation is also given in Winter's paper, and then the NI equals to 4 minus 2 divided by N. So just give an example. If you have 1 point, then you have 4 minus 2, you get 1. If you have 2 points, you get 4 minus 1, it is 3. If you have 3 points, 2/3 is what? 2/3 is 0.6666. Then you end up with 3.333, and the exact one is 3.4. Okay, something 3.4. Yeah. So it is approximation. So you just go to the table, that might be easier, and then 5 points on, etc. So the more number, the higher the value of the N, the higher the value of the NI. Okay, but again, maybe easier to just come to this table, and if you just want to go for a conservative one, you go for 4.0. That's it. Okay, now let's see here. The expression is given here. What is the thing which is given in here is actually using the, well, you're gonna see the alternative way of calculating the axial force here later. The point is that this one is going to be conservative. This is the full mobilization of the flange buckling, compression buckling load. In fact, the mode of failure may not actually looks like this. So elastic buckling, first of all, this is the elastic buckling of the column. If you recall, the elastic buckling part is there, and the inelastic buckling part is going to be another part there. And elastic buckling is just go up. This is going to be really high, right? So this could be crazy in some situation. So the PF equals to pi square EI over L square could be ridiculously unrealistic, because the beam might goes like buckling, into the inelastic buckling, or yeah. Alright, this is your beam. So moment and the unbraced length. And well, that depends. Okay, you are in this zone. Of course, the formula here is friendly. Okay, it doesn't give you the unrealistically high value. But if you are in some zone behind this line, alright, you know that elastic buckling is gonna give you like the overestimation of the axial force in the column, because in the top flange, which we idealize it like a column, because inelastic effects gonna come in and you do not have as high load as you anticipated by the elastic theory. So it is possible that the P can be estimated using the moment capacity divided by the h, where the h is the height of the cross section. So you can estimate the axial compression in the flange, compression flange, and you just need to make sure that the brace stiffness that you provide is going to make the compression flange mobilize the load to be that to be up to that level, which is the M over H. So the M over H is this one, right? So M is coming from here, right? And you're gonna get the benefit when you are in this zone. So M over H is going to be less than the P buckling, P flange Euler buckling in this situation where you expect the inelastic buckling. So this is we are coming down to the root derivations of this formula for the brace stiffness calculation. Anyhow, we are going to have a lot more after this one, but first at this point here, I think you understand that this point, the estimation, how it come from, and when you should use the PF computed from the elastic buckling theory, and when you should estimate the flange compression force from the moment, because your moment is not going along with the PF under inelastic buckling. But anyhow, you be on the conservative side, but when you are too conservative, you do not have a job. That's the thing. So okay, let's move on to the next point. Okay, erase this one. Should I? I just feel bad. It's a nice drawing there. I don't like to erase it. Okay. Now come back here. So this one works, and this one is the fundamental for the column brace design. This is the optimal brace stiffness. It is the optimal brace stiffness we have previously. You use this as the fundamental formula, and then we move over to here. The thing is that the axial force in the compression flange is going to be affected if we calculate the moment, right? It's going to be affected by the CB factor. And the CB factor here is something we have seen from the previous version, previous lectures, when I talk about the lateral torsional buckling, and the CB is the factor that affects the capacity of the beam. So the situation that we derived the lateral torsional buckling capacity of the beam was under the uniform moments. We have the pin supports, simply supported conditions, and the CB was introduced, because if you are going to deal with some sort of different bending moment diagram which is not the uniform one like this, you'll be able to resist more moment. So the CB was introduced for different kinds of bending moment diagram, where we have the very detailed discussion, another discussion. I talk alone, but I give you quite a detailed explanation on the CB before, so I assume that over here you understand what I'm talking. So the CB is a factor that enhance the strength of the beam. Okay, the lowest CB, the most conservative CB is 1.0. But when you change the bending moment diagram to some other things which is not uniform, then you end up with 1.xx or even up to 2.xx. So what is the what could be the issue that we have? The CB, as it increase the moment capacity, it's gonna increase the bracing force as well, right? Because the axial compression in the flange is increasing. So it is unavoidable that, well, if you gain something, you gotta pay for it. And if you have more capacity for the beam, it is the upgraded version from the beam under uniform load. This CB is going to come in, and if you want to have the full bracing from the case where you have the non-uniform bending moment diagram, CB is going to be introduced to here, to the fundamental brace stiffness, the formula here. So we have this one with the CB introduced. CB, as it is always greater than 1. That means you are going to require higher brace stiffness than the case we have seen before. No, just the case where we have the uniformly distributed load, not uniform bending moment. Okay, sorry. All right. Now, what else? Not only CB that is going to come border into this formula, you're gonna have the CD, and this is about this is a factor that comes in when you have the inflection point in between the span. So this CD is introduced, and then number of brace along the span is given, okay, by the CL factor. So one more thing is introduced. So these are the aliens that you never see in the column brace design, but when we talk about the beam bracing design, you have the CB coming in, the CL and CD coming in, but the fundamental is that this core part here, they are just the same thing. That just account for the buckling of the compression flange. Okay, so let's move to the next page. And this table just explain the N, right? The N subscript I. So you can pick up 3.41. Okay, we can derive this table using the numerical techniques. Just run the nonlinear buckling program subroutine. You have it, and that's a lot of fun. This chart is just a summary of the lateral brace design. Just keep in mind, we just come across the first part of the beam bracing design, which is the lateral brace design, but you know that the beam is going to suffer from lateral torsional buckling. So we are restraining just the lateral buckling, but torsional part is not yet restrained, and alright, it is going to be coming after this part here. Now, let's see. The brace stiffness is given as like an alternative between this and this. Alright, actually they are pretty much identical. The thing is that here CB times PF and MF over H. This MF is the moment. It is the calculated moment in the beam, and that maximum moment will determine the brace stiffness, and this MF could be less than the CBPF. Okay. Again, the PF comes from the elastic buckling, which is always greater than the inelastic buckling. And regarding to that fact, this will be very conservative. The lower the unbraced length spans, then this is going to be extremely conservative. But this one, you get the MF, and the MF incorporates the inelastic buckling, as the MF come from the buckling, the beam lateral torsional buckling limit states listed in the flexures chapter. So, okay, this one supposed to be lower. Should I call less conservative? It is still conservative, but the other one is more conservative. Okay, because we are not violating, we are not just using something that is below the requirement. It is conservative, but this is just it could be a sloppy way to do business. So if you don't want to spend time finding out the MF, or you are in the design office, so I understand that well, you need to produce a lot of design in one day, and you do not want to spend time looking back up to find the MF and so on and so forth. So you look at the flange, you see the dimensions of the flange, and you're going to say that the beam of this flange thickness and width will never buckle. I mean, the top flange will never buckle with this brace. So of course this one is going to guarantee that with even higher force magnitude, this one is not going to let your top flange buckle in any situation. Alright, so this is the difference. You may wonder, if these two are the same, why list them out like this? It is just to give like the possibilities for you to do the more refined analysis. But the other things are pretty much the same. The NI is there. This thing is equivalent to this thing. The CLCD, CLTD over LB over LB, all identical. Only one thing. We have the number 2. The number 2 here actually will be discussed on the right hand side. Okay. The factor of safety and all things will be discussed in the court part, but this is the recommended design. So we take the 2, this number 2 at this point here. I think it is quite important to talk about to understand the anatomy of the whole thing. So let's take a look at this one here. I'm trying to go down to that detail. If you recall, we used to make one Excel spreadsheet to show how Juras come up with what is this one? I think this is P critical over P, and this is the delta L over delta naught, and we start from somewhere there, and okay, you get a really ugly behavior with the beta equals to beta ideal, right? And later on you have it comes from the same, right? And even stiffer. What's gonna be the color? Okay, right, you just go back to the paper. You have it in your hand. You have the lecture note, you have the videos, you have everything. So it's a matter of fact that you just need to do all this. Just go back and take a look at it. Beta equals to 2 times beta ideals, and the last one is the beta equals to 3 times beta ideal. You don't get much from 2 to 3. Behavior is not improving that much. So as you can see that the bracing force is not going to reduce a lot, and the deformation is not going to reduce a lot when you increase the brace stiffness from 2 to 3. So the lucky number that we draw today is the number 2. Okay, and here is why the number 2 appears down here and there. Okay, it has nothing to do with this number 2, just for your information. So this is I equals to 1. And so on. So it has nothing to do with this. Nothing. Okay. This number 2 is going to be plugged into the NI. But the 2 we saw in here actually from the fact that it is appropriate, and it balance between 2 aspects, the economy of the construction and the engineering. We get good numbers for the engineering consideration, and we get the good behavior and cheap construction. Cheap seems to be a bad word. We should call it economy, right? It will be giving like a better perception about the thing. So okay, the number 2 is from this fact. 2 times, twice as much of the required ideal stiffness, the calculated ideal stiffness. So with the initial imperfections and in the considerations of the bracing force, you are still at the optimal point where the brace stiffness is not too high, not too expensive, and the behavior is good. Well. All right. So we see the overall things in the stomach of the beta L2 is understandable. Y is from the NI is understandable. This part is understandable. C, L, C, D, LB. All right. Okay, and the explanations on all of these are just given in the same place. Fine. But actually I explained everything already. Now regarding the strength of the brace. Discrete bracing and relative bracing. The discrete bracing is the point bracing. and relative bracing is the panel bracing, which is the vocabulary proposed by ISC 2016. So the 2016 version code, I showed you that already, right? And it just require you to call it in a different way, but okay, point or panel. And the force is found to be higher for the discrete bracing. Actually, this is going to be fun to just run the model we have, the code we have, and we can investigate and look into how much required bracing force is going to be. Yeah. And I think you still remember the number, like 0.004. This is like 0.4%, and this is 1%. Why is the force in the relative bracing? Why is it higher? It seems to be a good morning for many people, right? So let's take a look. If you have the column like this, and you brace the column like this, okay, and this is a relative bracing when you just put this diagonal brace. The brace gives the relative stiffness between this level and this level. So it is like you are giving the spring. Where is it? Giving the spring between two levels. One level. Here. It's like this. This spring is representing the diagonal brace. So this spring, well, the stiffness of this spring is going to be calculated from even this is the relative system. If you have the maybe the counterpart system, which is the point bracing, or so you brace it with something like the wall or some stiff support. Okay. Force that develops in here are going to be greater than in here, because these 2 points can be moving together, right? And force in the diagonal brace will not be as high as the force in here that takes the absolute deformation, because you are refer the total deformation in the spring is referred to the zero fixed point, whereas the force in the brace here is referred to, if you have the U1 here and if this is U2, then it is just the relative numbers between the U1 and U2. So that is the reason why the bracing force in the discrete bracing is higher than the relative bracing. And okay, now we get the part beta star. We come to here. In the design provision, you are not just finished at the beta star. The beta star is the recommended value that gives you this behavior. That requires quite a small deformation to mobilize the full bracing force. But that's still the derivation. So that derivation does not account for any imperfection, any material problems, any erections, imperfections, any etc, etc, etc. That means, okay, the strength reduction factor is not there yet, the force, the load factor is not there yet. Okay, so now if we look into the design provisions, specifications, the recommendation looks like this. Well, this paper is old, but okay, still useful. So AISC, RFD, as we used to see, the beta that you need to provide it, how did I say to provide it? Grammatically incorrect. So the provided beta has to be greater than the theoretical beta L star, right? And you incorporate the factor, and this is the strength reduction factor. Again, you got to keep in mind that this beta is actually calculated from the moment. Your moment is coming from the factor load. Alright, so that means the load factor is already embedded in here. Alright, so you do not how to say, you don't get confused. You understand why. Is it just divide by the feed, the reduction factor, and where is the load factor? The load factor is already from the beam design. Okay, it's there already. So if you apply the load factor another time, it is redundant. You don't do that. You just take the beta L, which includes the load factor. I should write it down properly. Write down nicely. Give me just a few seconds. The load factor. The load factor is already absorbed the load factor is already absorbed in the moment which is used for beta star L calculation already. And this is for the LRFD. Oops. Okay, to make it clear, to avoid any confusion, okay, so it's there. For LRF, the load factor is already absorbed in the moment which is used for beta L calculation already. Okay, so you just need to divide by 0.75. The thing is that you're gonna see this. You will feel like the internet just disconnect you all again. I encourage you to come back and watch the YouTube, because that's gonna make your life easier, and it's going to frustrate you like this. I am frustrated as well to have the internet connection like this, but I think some device in my house, my mother's iPad, my brother's iPad, or some crazy device just mess up the whole Wi-Fi system, and that always happen in the morning, just in the morning only. I think when the device is turned on, and that's mess up the whole thing. Alright, okay, but the point that I'm going to make is that you're gonna feel like, hey, this beta L and this beta L, you feel pretty much that they are alike, but they are not. Okay, I think you need to emphasize, and you need to make sure that this point is clear for you. You might think that they are alike, but they are not, because if they are alike, beta L divided by phi, and phi is equal to 0.75, so that makes what? 0.75, 1 over 0.75, that is 1.3333. Yeah? So you feel like this case is equals to 1.33 beta star L, whereas this one is 2.00 beta star L, and you feel like, wow, the ASD is super conservative. In reality, they are pretty much the same. So if you look at this, where 2 is a factor of safety, or safety factor, they mean this 2. But in fact, how does the 2 come from? The 2 come from the load factor being 1.5. Why? Why is the load factor here? Because allowable stress design, the internal force moments are computed from unfactored load. Alright? And as you have the unfactored load in your design, at this point here, when you compute the factor of safety of the system, you are going to need to account for two things: the uncertainty in the load and the uncertainty in the material. The uncertainty in the load, you cannot expect how the structure will be used. Is it going to be used properly or not? So the load factor for the load factor not for anything is introduced, and it is about 1.5. Why 1.5? 1.5 is one sloppy number that people just can come up with very easily, and it is quite conservative. So if you think of the 1.2 dead load plus 1.6 live load, 1.5 is somewhere which is close to 1.6. It is producing quite conservative number, especially when you are dealing with the larger and larger span structures. You are coming actually close to 1.2 dead load, because the dead weight of the structure is the bigger contribution comparison with the live load. But you are using the number which is close to 1.6, which is in the conservative side. So you have a larger contribution of 1.2, but you rather use the 1.5, which is very close to 1.6, in order to average of this. In fact, to write it down nicely. 1.2 date plus 1.6 life. So here the simplification is the 1.5 times the date and the life, right? Which this one is going to be bigger than 1.2 to 1.6 because the fact is that the date is more than the life, right? If your span is really short, okay, you might bump into the problem like that, but in normal structure you will rarely find a case where you have the date load less than the life load. Okay, so they are different now. You cannot just do things like this. Okay, these two beta L are coming from the different bases, so be careful. And if you want, you just pretend that there is no allowable stress design and just go for LIFD if you don't want to confuse yourself between two systems. Remark, okay, I put the remark here that the beta star L LRFD incorporates load factor already. Whereas beta star L ASD is calculated from unfactored load. In other words, they are different. Okay. 9:30, 1 hour already. Clear enough. Now it is a lateral brace design example. You just can go through all of these. It is just documented information about the design example. So it is just all the way back of these documents. Okay, so Juras provides everything here. This is just the appendix part, and you can see how the stabilities or the brace are properly designed accordingly. Okay, so that is well documented already. We'll come back and to here. So we finish up the matters about the lateral bracing of the beam, and another mode is the torsional bracing. And again, the code also already said so, and I want to emphasize. And the beam and the truss actually are the same thing for my eyes. The beam, the flange is a top and bottom chords, right? The web is a diagonal chords in the truss, and that's it. So the design methodologies or the design techniques, the idealization of the problem is actually identical for beam and truss. And if you want to design the truss, especially when, well, I found that very painful in the past. Actually, when at the time that I didn't teach this course, well, because the PhD graduates before I get into these matters in the stability. I did just finite element and not coming too much into this business stability. So in reality, the PhD graduates actually not the guy who knows everything, but it is the peak time of someone's life. This is not about the steel structure, but okay, just something. It is a peak time of someone's life that he or she could have like too much confidence. So it is a overconfident time that one graduates the PhD and one's gonna realize that he or she doesn't know much actually from the PhD. It's just a degree. It is just a degree that proves that you have done, you know how to do research, how you formulate the problems, how you attack the problem systematically, how you justify your work scientifically, right? That's the PhD. But there are plenty of things that one do not know. A bunch of things to know in the world, to learn in the world, right? So, well, at the graduation of PhD, one is gonna feel like he or she knows a lot, but in reality, he or she doesn't know a lot as much as they feel. In my experience, I think I learn a lot more when I teach than when I was in school. This is the beauty of teaching at AIT. I think or maybe teaching at other universities in the world will enrich the instructor. So before coming into the class and before being able to crystallize the knowledge to make it good enough for the student to learn, I think it's been passing a long way in order to make it robust like that. And the point I want to make is that, okay, at the point that I graduate as a PhD, this is not my expertise, because generally for a PhD you know just a few things. That's the main point. And I think this could be the pain for many people in the business. I think people graduate, people enter into the business, and this is just a very classic examples. Like the roof truss, I think for all of us must at least once in a lifetime design the roof truss. This is unavoidable. You're gonna design the roof truss. If you are a structural engineer, at least one roof truss in your lifetime. The point is that the roof truss is prone badly to the instability, and the practice of the roof truss design generally, people will say that, okay, it is well braced. All right, well braced. Okay, you can say so, but who take care of the brace design, brace analysis, second order analysis also? I don't think many people really understand how this is taken care of. So the roof truss design, and generally I think it is not done in the right way. The span for the roof truss, especially when you do it for the factory, the roof truss could span over, let's say, 20 meters is just a piece of cake for the roof truss. I don't think that is the good example. It is just a very simple assignment like the homework in the university. But in reality, the roof truss is gonna span over like 30 something plus meter, 30 to 50 meters. And the thing is that the roof truss is actually the expensive component in the construction of the factory. Yeah. And since we have so much time, we can talk about good things, which might not be advanced steel structures. But, I insert the page. What kind of page? Graph paper. Yeah, done. Okay, so the roof truss like this. This is a factory. So in a factory or warehouse, it's gonna be pretty much like this. You have the floor slab. In Thailand, the soil is very soft, so you have a bunch of piling works to make sure that you do not have very bad settlements in the factory floor slab. Space here is around 30 to 50 meters. Of course, you do not want to have columns in between because you're gonna put the stack for the storage, or you want to put the equipment on the machine in the factory floor area. So generally there is no span, no column in there, and the roof truss you have gonna span over 30 to 50 meters, which is quite challenging. The thing is that the construction of the factory is a lot, and people might not take it so seriously in the stability point of view. The thing is that the 30 to 50 meters span, how do you incorporate the stability issue in the roof truss? I don't see the calculations of the serious brace calculation in the roof truss, the good one. So the roof truss actually includes something like this. When one design, okay, I'm gonna talk about that. When one design the roof truss like this, you can just use the manual calculation. You compute the load per unit length, right? And then you can analyze it like a simply supported beam. You get WL square over 8. WL square over 8 turns out to be the internal force in the top and bottom chord, and the shear force is going to be supported or absorbed by the diagonal part of the truss. So that's it, as simple as that. You have compression force, you have tension force, you have something in the diagonal, whatever, right? And then what you design the chords, compression chords, you design it assuming that this is the unbraced length, right? And what else? Tension is easy to design. The point is that the global behavior is not considered. You might think that you have the diagonal like this, so the buckling will be just about this, but no, it could buckle like this. It could buckle like this, right? If you brace at the middle part, the midpoint here, you might have your roof truss box like this. So things like this is quite interesting, and sometimes the analysis or the design is too simplified too much, and you might not get the behavior that you wish. You think that okay, it's gonna buckle, form the full buckling length, half side buckling like this, but no, the global behavior is coming up in that view. So that's why you're gonna have a sub truss, and you're gonna feel like, why do we need the sub truss? maybe subtruss is in the middle part like this. It is just to prevent the out of the truss plane lateral torsional buckling. The truss just fell in the same way as the beam. So lateral buckling is caused by the top chord under compression, and then as the top chord deforms, it goes laterally. The torsional is coming along as a result. And the roof truss is actually the important component for the cost of the factory. So as it is steel, and the erection is needed, right? So the fabrication is expensive already, the erections, painting work, and so on and so forth. So the steel is weight multiplied by unit cost. So the paint comes along the weight. The material, the fabrications just come along the weight. So generally, the structural engineers try to minimize the cost or the weight of the roof truss in the design. And the point is that the effort to do the value engineers of the roof truss, when it is too much, then you might be in a great deal of risk of the structure. So just be very careful. I think the knowledge we had here, we learn about beam, we learn about bracing. We should be able to design the bracing system of the roof truss. Okay, so you can anticipate from the beam formulas, from the beam derivations, you can anticipate how much maybe the cross section, how big should this cross section be, because you have no idea how much force right now. You don't have any idea about the force, but when you learn of this bracing, if you look at the top view, you're gonna see something pretty much like this. Oops. Right, this is the top view of the factory, and you will provide the brace like this, as you can see from the top view, to restrain the other roof truss. Okay, so the thick line represent the the thick line represent the roof truss. Okay, so other roof truss will be locked to the panel here. This panel will be used for both wind, right? It is used to restrain the whole structure against the wind load, which the exposure area of the factory is quite a lot. So you need to restrain against the wind. That's the first thing. And second thing is that this provides you stability. So the brace that you design has to account for two things. You take the wind and you add up with the force you expect for the stability point of view. But now, what do you expect for the internal force for the stability? Internal force in the brace, that is for the stability. So you see. And if I give you an example, maybe you have a lot more this way, but maybe it's gonna look like the repeating cells like this. The factory generally like very long, 200, a couple of hundred meters long. So in every maybe 4 bays, you provide one bracing bay. One bracing bay is going to lock the other. Well, in total you have 1, 2, 3, 4, 5 trusses, roof trusses, and you have the lateral, the orthogonal direction truss in the red. This one is just used to lock your main truss. So if the green is a cross section of the main truss, if I take the cut like this, right, and at this point where it is connected to the red. So the red is going to come in like this and come in like this, right? Well, the red part must be able to transfer the load, which is going to be from the instability of the top cord. Well, we lock to the bottom cord as well because we need to restrain everything against the torsional buckling. So the bottom cord is also locked. Right, and then, okay, well, you can put the details of the... In the design business, people always call it this way, T1, T2. And people just going to understand that T2 is like the secondary truss that is used for the stability. So this is the T2. The green is a T1. So we need to restrain the T1 truss cords such that it doesn't move, and that T1 is going to mobilize the full bending, full moment carrying capacity. The thing is that the T2 shouldn't fail, right? Because the T2, this span is sort of like 6 meters in general. So 6 meters is not small, and T2 could buck. So the diagonal brace and the truss-like configuration is provided to T2. Many times people have no idea how to design for T2 because you do not have internal force in T2. So we just repeat the cross-section of the T1 in the T2, whereas the T2 doesn't really have, it has nothing to do, but it's just the bracing system. So the force in the bracing system was supposed to be much lower than the force you have in the primary system. Now, you have 4 repeating bays, and 1 bay is braced. Okay, you can find the size of these bracing members using what? Generally, the bracing member is the tension member. So if one is bracing, another will not be working, right? It depends on the direction of the force. So if you have the panel like this, and if you apply force like this one under compression, this one tension, the tension one is going to carry the load. Whereas if you have the load in the opposite direction, then this one carries the load because it is a tension, whereas this one is a compression. Compression is going to form some sort of like elastic buckling. There is no permanent deformation in your truss as it is really in your brace as it is really slender. So the brace is generally made of maybe the deformed bar or the tie rod, whatever, maybe the cable. And these components are not going to be experiencing the yielding under compression because it's going to buck, and as it bucks, and it doesn't engage the force. Okay, so what I'm trying to say is that only one out of 2 is going to carry the load. Then when you design for, well, in your design, you got to design such that only one can take or can contribute, okay, the stiffness to the requirement, to meet the requirement. You don't take 2 and then you just give them the equal amount, because the one under compression is not going to work, and then you'll be in trouble. All right. So in the design, when you design, you just imagine that you have just one piece, okay, and one piece has to carry the whole force, and that will be under the tension mode only. In the reverse direction, that tension is turning into compression, and then it does not contribute anymore. So the force is handed over to another one. But the thing is that the bracing force we need in here. Oops. Okay, I put this one. The design of this brace has to be accounted for 1 truss, 2 truss, 3 truss, 4 truss, 5 truss. Very interesting, because you are going to brace in total 5 top chords. 5 top chords. Total force is going to be the 5 times the PF, or the 5 times the moment divided by the depth of the truss. If your design, you just make it for 1 like this, how about the rest? So you are like 5 times shots, right? So this design has to account for all trusses in the same repeating cells. Okay, and likewise for the bracing force, so the diameter of the tie bar, tie cable is determined from that. Also, the force is going to be determined from that. And now the T2, how is it designed? As you know, the maximum force in here, you know the component in this direction. This component is going to be smaller and smaller as it go far away, right? But you just design for 1, so you just design for this one. So the maximum orthogonal force in this direction is going to be used for the design of the T2. And the size of the top bottom chord of T2 can be determined accordingly. I think this is quite a fun thing to do. Maybe in the next year I made like I get some sort of real roof truss, and then we can try to design this roof truss in next year class. But the idea, the concept is just this. The more than this, it's just the number crunching, which is just the time wasting activity. Okay, but all of this just gonna make yourself make you feel better when you design the roof truss structure for the large span structure like this, exhibition hall or the factory, so on. The best way, maybe even better way, is to make the 3D model. 3D model will be more accurate, of course. So you put the 3D model of the roof truss and turn on second order analysis, right? Second order analysis, turn on nonlinear geometry. Nonlinear geometry is turned on, and then you put the brace stiffness that is guided by AISC specification. So you put it in, and then you check. So you run the buckling analysis. You apply the distributed force on the roof truss, and you run the buckling analysis. You'll be able to get the buckling load and see if it is enough for your purpose or not. If your W, which is uniformly applied over the truss, is not enough, then you can look at which particular component is suffering from the buckling, and then you look at that and try to fix it. So just keep fixing it. Well, but the fundamental requirement is that the moment from gravity, not yet talking about the from stability issue, just the gravity load your truss structure needs to be able to withstand. Otherwise, it's gonna fall by just the gravity aspect. It does not even mobilize the buckling. And sort of unbelievable. We still need to come back to here. So it cannot be wrapped up today. I thought that it's gonna be wrapped up, but anyhow, this is an important component, and you don't want to go for the cheap one, but not safe, and you do not want to go for the super expensive one. Well, even though it is safe, but you should not underutilize the structure. You shouldn't over design too much, and it is a waste of the material. Okay, so we can continue tomorrow. So we will not have only 28 classes then. We're gonna have the 29th class tomorrow. Probably, not just probably. I think we should finish it up tomorrow.